All right, so basically for the graduate students, I wanted to do a proof of this. Um, okay, so Y bar, as we know, is the analytic solution of the problem at a particular time step. And then Yn is the actual solution to the problem at the particular time step. Okay. So
Mhm.
Y bar is the analytic solution and Y is the approximated solution. All right, so Y bar at X plus H is equal to Y bar at X. I don't know why this thing is acting up again. There's nothing I can do. Plus H times Y bar prime at X. This is at Xn. All right, plus H squared over 2. And then this is Y bar double prime evaluated at some Cn. So that's exact because we've included the error. Okay. Now Y, so that says that Y bar n plus 1 is equal to Y bar n plus H times Y bar prime at n. And we know that Y bar from our differential equation is the solution to Y bar sub X. So that's just F. So I can, instead of just putting in Y bar prime here, I can put in F at Xn, Yn bar, and then plus H squared over 2 Y bar double prime at Cn. Okay, so this is exactly what we have for Euler's method. So now Euler's method is Y n plus 1 is equal to Yn plus H times F at Xn, Yn. Okay, so what's the difference? This right here is exact. Well, let me put it on the other one. Yeah, these two, this one is exact. So this one is exact. And then this one is what's calculated using Euler's method. Okay, so therefore, there we can calculate the error between the two. So we take and we calculate the error between the two. We get Y n plus 1 bar minus Yn plus 1 is going to equal Yn bar minus Yn plus H times F at Xn Y bar n minus F of Xn Yn. Okay, plus our error, which is H squared over 2 times Y bar double prime at Cn. Okay, so now from the beginning part of the class, Lieutenant, I don't remember if you were here, but when we were first deriving the errors, But this, we are calling this thing en plus 1. So
Okay.
en plus 1. And this thing we call en. Okay?
Mm-hmm.
Get en plus 1 is equal to en plus h times f of xn y bar n minus f of xn yn. And then we still have the h squared over 2 y bar double prime at some cn. Okay, so now when I plow through with absolute values, I end up with less than or equal to. And so now I have h, and then I'm going to get m times the absolute value of y bar, of xn, of m, that's right, y bar n minus yn, and then plus h squared over 2 of absolute value of y bar double prime of cn. So now where did that come from? That's a hypothesis. So if we go back in our hypothesis here, all right, assuming that the analytic solution of the initial value problem, all right, such as looks like this, and that the difference between YA and YB for any solution is less than or equal to a number M times the difference between the two solutions. So this M is from the hypothesis of the theorem that we're proving. Okay. All right. So now I get the absolute value of en plus 1 is less than or equal to the absolute value of en times 1 plus h times m plus, because I factored out, this thing right here is now again en. So this thing right here is, this here is again en. So I can factor it out. Plus h squared over 2 absolute value of y bar double prime at cn. Okay, so let's look at that. This says E1, the absolute value of E1 is less than or equal to the absolute value of E naught times 1 plus h m plus h squared over 2, the absolute value of y bar of some c naught. Okay. And then we have the absolute value of E2 less than or equal to the absolute value of E1 times 1 plus HM plus h squared over 2 absolute value of y bar double prime of some C1. Okay. And this is now less than or equal to, in brackets, the absolute value of E naught, because E1 is less than all of that. So that's E naught times 1 plus HM plus h squared over 2, the absolute value of y bar double prime at C naught. Okay, so that part right there, this part right here is just what E1 is less than or equal to. But that's still less than or equal to 1 plus HM plus H squared over 2. And I'm going to call this the norm of Y double prime at C1, where I'm going to define the max 0 to n, the absolute value of Y bar double prime of Cn is going to be less than or equal to the infinity norm of Y bar. Okay. All right.
Excuse me.
Okay. So if I keep doing this, which I'm not going to, because so as you can see, what I did was I replaced, here was E1, and I replaced E1 was less than or equal to this. So that was E1, which was here. Okay. So I get the absolute value of En is going to be 1 plus H times M to the nth power, because each time this is 1. So now you can see you have E naught 1 plus HM squared. Okay, from this one. So therefore, I'm going to get the absolute value of E naught. And then I'm going to get plus 1 plus HM plus dot 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 plus 1 plus HM to the n minus first power times H squared over 2, the infinity norm, this should be Y bar of Y. Okay. All right, so now that I have that, you should recognize this M doesn't look like an M. My M's just really are pretty pathetic. Let me make that look like an M. Okay. So you should recognize a geometric series here. So for a geometric series, one plus R squared plus all the way up to R to the n minus 1, which is the sum, okay, equal 1 to n of R to the k minus 1 is equal to R to the n minus 1 minus 1 over that's right, over 1 minus R, provided the absolute value of R strictly less than 1. Actually, it's true if it's not a convert. I'm not worried about the full series. I'm only worried about the partial series. So this is true if R is not equal to 1. I only worry about convergence when R is equal to 1 or minus 1, but I don't have an infinite series, so I don't have to worry about that. So I get that the absolute value of En is less than or equal to 1 plus h times capital N to the n times the absolute value of E naught times plus, here I'm going to get 1 plus hm raised to the n power minus 1, and all of that is over h times m times h squared over 2, and again the infinity norm of the second derivative of y. Okay, now I gave a lemma last time, so I'm going to scroll back just a little bit. So here was my lemma. And my lemma was that 1 plus x to the m was less than or equal to e to the mx. And we just did, if you just do a Taylor series expansion, and you only take the first two terms, it has to be less than the entire expansion. So I'm going to use that now. Just wanted to refresh your memory on the lemma. So by lemma 1, one plus h times m to n is less than or equal to e to the n times h times m, which is equal to e h. This is x naught, xn minus x naught. Remember, n times h is the length of the entire interval times m, which is less than e. The end interval is b minus x naught times m. You tired?
No.
The absolute value of En then becomes less than or equal to big bracket e to the b minus x naught times m minus 1 over m the two h's divide out, so I just get h over 2, and then I get the norm y double prime infinity. Okay, so that's the end of the proof. So what does that mean? It basically says if you decrease the step size by a half, then your error should decrease by at least 1/2. So note, if you decrease step size h by a half, then your error should decrease by at least 1/2. Okay. All right. Any questions about that? Now, what is this infinity norm that nobody has yet asked me about? I'm kind of excited. Nobody said anything. Nobody said anything. I'm like, what in the world? Okay, so the infinity norm of y bar double prime at x infinity is just the max on the interval from A to B of the absolute value of the second derivative of y of x. So the infinity norm is to find look at all the different points and find the max of the values that are in those points. Okay?
Okay.
All right, so that's what the infinity norm is about. And one way that you can deal with that is y double, and actually, I don't know why I have x's. These are t's. Oh, let me go back. Where did I stick an x? I know I saw x somewhere. X here. That's a t. This should be f. Oh no, I was doing the proof in x. I did do the proof in x. Okay, then that's an x. Leave it at x. I did the proof in x. Yep, I did do the proof in x. Where is that? Okay. All right. So now here you're given this problem. So y double prime of x is equal to the derivative with respect to x of y prime of x. But that is the derivative with respect to x of f of x and y, where y is a function of x. So that says to take the partial of f with respect to x of x and y, and add to that the partial of f with respect to y of x and y. But I got to multiply by the derivative of what's inside, which is dy dt, which is simply just f of x and y, where this piece is dy dx. Okay, so I know you guys haven't seen this in a long time. I think this, but f is a function. This is Calc 3. F is a function of x and y is a function, sorry. F is a function of x and y is a function of x. So we had to use the chain rule to get the derivative of f with respect to x. You have to go out the one branch plus out the other branch, but then this branch would have given you dy dx. And this branch gives you the partial of f with respect to y. And this branch gives you the partial of f with respect to x. Okay, so just so you can see that that's one way of, if you don't know how to, if you're not quite sure how to find a maximum for y double prime, here's a way that you can do it, okay? All right. All right, round off error. Global error was 6, 7, Okay, so round off error gets propagated because if you rounding your solution if you find y1, I'm just going to scratch here. If I find y1 is equal to y naught plus h times f of x naught y naught, and I'm chopping. Well, I'm going to do round off error. So I have round off error here. Say I'm rounding to whatever 6 digits, 4 digits. Then I take and propagate that error in the y2, f of x1, y1. I have more round off error. So round off error propagates off of every iteration as we are trying to find our solution. Okay, so round off error must be considered when choosing your step size h. Why? Why? Why do we have to consider round off? Why do we have to consider round off error when we choose our step size h? Anybody have an idea? As h becomes smaller, more calculations are necessary. And more round off error is expected. So if I make h very, 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 very small, I might be getting a better approximation for that next iterate based on h being small, and I'm looking at us going out the tangent line in order to get the next value. But if it's too small, then I'm doing more h's. Remember, h is equal to b minus a over n, or xn minus x naught over n. So as n gets bigger, h gets smaller, I get more round off error. Okay, so let's look at this solution. So here is what we have. So we have yn plus 1 is equal to yn plus h times f of xn yn. And then y naught, y of y naught is equal to some number alpha. And this is the numerical solution without round off error. Okay. So now, if we have round off error, we get un plus 1. This is with round off error, is going to be un plus h times f of xn un plus my round off error is delta n plus 1, and that's at each level, and my u naught is equal to alpha plus delta naught. So I round it. So now if my alpha, if I want my y naught to be 5, and then my u naught is going to be simply 5. But if my alpha turns out to be something like the square root of 3, then obviously I'm going to have round off error when I move to the second problem, because I'm going to truncate the square root of 3 in order to approximate it. So this is numerical solution with round off error. Okay. All right, so how do we deal with this? We still get the same thing as we had before, but this time we now are going to, so I'm going to write this. I would just cut and paste, but you guys would be behind the 8 ball with trying to catch up. So I'll just, okay. So we get y bar n plus 1 is equal to y bar n plus h f at x n y bar n plus h squared over 2 y double prime y bar at some cn. Just as before, that's the exact solution. Okay, and then we have y bar n plus 1 minus un plus 1 is going to equal y bar n minus un plus h times f of x and y bar n minus f of x and un. And then I'm going to have plus h squared over 2, just like before, y bar double prime at cn. But this time I'm going to have my round off error. So this is the new term. So here's my new term, right? And I can do the same thing as I did before, go through this whole thing. And then I can start looking at the errors. En plus 1 is going to be less than or equal to the absolute value of En. And that's going to be times 1 plus h times capital M plus the absolute value of h squared over 2 times y, oh, I don't want that there. Oh, I don't want that there either. Times y, oh my goodness. Thank you. Y bar double prime at Cn. Now you can see where I maximized that and came up with the infinity norm minus the absolute value of delta. And we can keep going and do the same thing as the previous proof. So what's different? We're going to get the absolute value of En. It's going to be less than or equal to e to the b minus x naught times M, absolute value of E naught, plus, I'm going to get E to the B minus X naught times M, minus 1, just like before, over M times H. That's going to be multiplied now by H squared over 2, the infinity norm of Y double prime bar. But now I have times minus the absolute value of delta. So now I get the absolute value of U bar N minus UN is less than or equal to E to the B naught, B minus X naught times M times the absolute value of delta naught plus E to the B minus X naught times M minus 1 all over M. I'm going to get rid of the H because they're going to cancel. I'm going to get H over 2, absolute value of Y bar double prime infinity, minus absolute value of delta naught over delta. I think that should be delta naught. This is the biggest delta over H. Okay, now there you should see there's a problem. So as you can see my problem here. Okay, so the limit. So first off, we see that our error bound is no longer linear. In H. In fact, the limit as H goes to 0 of that last term, H over 2, the infinity norm of Y bar minus the absolute value of delta over H goes to infinity. So therefore, we clearly need a lower bound for the step size H. Okay. So we want to figure out how to do that. We want to let E of H be H over 2, the infinity norm of Y bar double prime, minus, why somewhere I have a minus and there should be a plus. This should have changed to a plus. Y'all. This should be a plus. That should be a plus. This should be a plus. Okay, that's where I lost it. Let me put a plus in my notes. Okay. All right, so this should be a plus absolute value of delta over H. So E prime of H is just 1/2 infinity norm minus, here's where the minus comes back, delta of H squared. And we set that equal to 0. And we find out that H squared has to equal 2 delta over sorry guys. The infinity norm of y double prime infinity, or H is equal to the square root of 2 delta over infinity norm. All right. So for EH, to be a decreasing function, then H has to be bigger than that thing. Okay. So if H is actually smaller than that, then we tend to increase the error and get a problem with a round off error. Okay. And our hope would be that the absolute value of all the deltas is less than that one particular delta. Okay. All right. So that is Euler's method. I think that you guys have a good handle on that. Let's see. Okay. Let's look at improved Euler. Okay, so if you remember Euler's method, so let's go back to Euler's method for a moment. So Euler's method said, here's my function. Let's bring that down a little bit. Okay, here's my function. And I know the value at x naught. Here is y naught, and I want to go to x naught plus h. Now, the true value of f of x naught plus h is right there. So right here is the true value of f of y of x naught plus h. That's the true value. But what we instead are going to do is we go out the tangent line to a value right here. And we would take that value as y1. Okay, so this is the error, and I made it very prominent. Okay, so the error there is y is error. So the true solution, which is y of x naught plus h, is there. The value that Euler's method is going to give you is the green one. Okay. Snatch this picture. Put it right over here. Okay. So improved Euler says instead of doing that, what I'm going to do is I'm going to first compute K1, where K1 is the slope. So here, as you can see, so first thing I'm going to do is I have y naught is some number, let's say alpha. And then we're going to get a first estimate, which I'm going to call y, I'll call it un plus 1. Un plus 1 is going to be y naught plus h times k1, where k1 is equal to f of xn x naught y naught. Okay, so k1 is the slope of the green line. So K1 is the slope of the green line. So instead, I'm going to call this value UN plus 1 or U1. So let me just call this U1. So this is going to be U1. So U1 says ride out from Y naught out the slope and get an approximate value. So U1 is our old Y1. Okay, then it says find now the slope, or f of x, find the slope of what we're going to call K2. Is going to be f of my x naught plus h, which is my x1. So f of x1 and u1. So now I'm going to find a slope at that point. Okay, so whatever that slope is. So now I'm going to find the slope at that point. So I'm going to evaluate f of x naught y naught. So therefore I'm going to get a slope, and I'm going to see what the slope is off of this point. Okay, so there's some slope coming off of this point that is f of x naught, f of x1, y1. Okay, so K2 this is the slope of the gray line. Then I'm going to average the slopes. So if I average the slopes, it's like taking two vectors. So when I average them, I get something that looks like this. Okay, so I'm going to average them and use that slope and my original value to get my y, which is going to be this value. So this is now going to be y1. So now y1 turns out to be y naught plus h, and I'm going to average them, k1 plus k2 over 2. Okay, so how do we write that? So our improved Euler is as follows. So here's the algorithm. So of course we start off with start with alpha x and x naught. Well, x naught is alpha. No, it's not. We start off with x naught, xn, n, and then we calculate h and alpha. Okay, so here, y of x naught is equal to alpha. So we choose h is then going to be b minus a, I'm sorry, xn minus x naught over n. And then we're going to, for I equal to 1 all the way up to n, u is going to equal, sorry, I'm messing up here. Let me add something. Y is equal to alpha. Okay, so u is going to be y plus h times f of x and y. Oh, actually, let me compute that first. So let's do k1 is f of x and y. Then u is equal to x plus h times k1. Then k2 xp is equal to x plus h. Then K2, oh, that's what I know what I'm doing wrong. Okay. K2 is equal to f of x plus h u. There we go. Then y is equal to y plus h over 2 times f times k1 plus k2. So that's my new y, and now I can let x n, or my new x is x plus h. Oh, let's print it out first. Let's print so also go back here. I want to print okay. All right, so that's the improved Euler. And improved Euler is by far much better than the regular Euler. Okay. There's also a backward Euler. Okay, so backward Euler is, instead we're going to have, if we have y at x minus h is equal to y at x minus y prime at x times h plus y double prime at c h squared over 2, then we could see that y at y at x, oh yes, okay, now I know why I'm confused. So this should be y at 8x is equal to y at x plus 1 minus y prime at x plus 1, or x plus h. Y at x plus h minus y prime at x plus h times h plus y bar double prime at c h squared over 2. So that says that y at x plus h is equal to y at x plus h times y prime of x plus h. Now we know that y prime is equal to f of x and y. So this is y prime at x is equal to f at x and y. So this now says that y of x plus h is equal to y at x. This is approximate. I threw away the error. Plus h times f at x plus h, y at x plus h. In other words, y n plus 1 is approximately y at x n plus h times f of x n plus 1, y n plus 1. So what do you notice about backward Euler? What do you notice about backward Euler?
Is approximating the f of h plus.
What did you say?
I think is approximating the f of y s plus h. Is an approximation. I don't know. I'm
Okay,
not.
you're on the right track. You're on the right track. This is an implicit method.
Okay.
Basically, you need to know f at xn plus 1, yn plus 1 in order to find yn plus 1. Okay? So that's a difficult problem there. All right, that's, how do you do that? All right. And so this particular method is what it is actually implicit. It's what's the word I want? It is unconditionally stable. We don't have to worry about the value of h that you choose. But it can be difficult. So for example, so here's an example. So y prime is equal to xy, okay? Y prime equal to xy. If I used forward Euler, which is the standard Euler, we would get yn plus 1 would equal yn plus h times xn yn. Okay? And as you can see, you get yn plus 1 turns out to be 1 plus h times xn yn. And this actually, so you can easily see the solutions grow.
Okay.
All right. But what is the solution? Well, if I had dy over y is equal to x dx, then I get that the log of y is 1/2 x squared plus a constant. So I get e, take y, so I would get y turns out to be ae to the 1/2 x squared. So that's the solution. So I expect them to grow. Okay. But if I use backward Euler, uh-oh. Okay. I would have yn plus 1 would equal to yn plus h times xn plus 1, yn plus 1. So now I get yn plus 1 minus h xn plus 1, yn plus 1 is equal to yn. So now I get yn plus 1 times 1 minus h xn plus 1 is equal to yn. So now I get yn plus 1 is equal to yn over 1 minus h times xn plus 1. So this is the backward orbit formulation. Okay, should still give the same answer.
Okay.
But here's a problem. Y prime is equal to x squared sine y. Now we have a problem. Because now backward Euler is now hard. Because now you have yn plus 1 is equal to yn plus h times xn squared, xn plus 1 squared times the sine of yn plus 1. And now you got an issue. Okay, so backwards Euler works when you can actually solve for the yn plus 1.
Okay.
All right, but when you can't, you have an issue. It's hard. Okay, so on Thursday, we will be doing the Runge-Kutta method. Okay, so we will be approaching a whole new method, which is the Runge-Kutta method. And we'll talk about error and all that kind of stuff for the Runge-Kutta method. And then after Runge-Kutta, we will look at Runge-Kutta-Fehlberg, and then some multi-step methods. Multi-step methods are much better than regular, just single forward step methods. Okay, I have 2 minutes. I may as well start Runge-Kutta. All right, so for the Runge-Kutta method, and this needs to be a period. It won't take that. Okay, I'll start it next time. I'm going to start it next time.
Can you scroll up a bit? I'm here to get the last